Hello, and welcome to Mary Spring Nature Center's Tuesday Talks. I'm John Fromer, your host and the program director. Today's talk is generously sponsored by Camden River House, Camden National Bank, and Rennie's A Maine Adventure. Mary Spring is open every day of the year, dawn to dusk, free of charge. And you can visit Mary Spring online anytime at maryspring.org on Facebook, Instagram, and LinkedIn. Mary Spring's mission is to practice, teach, and advocate sound principles of ecology, conservation, and horticulture in order to protect our natural environment and to provide natural landscapes and cultivated areas for public enjoyment. There are many benefits to being a member of Mary Spring Nature Center, including free admission to our spring, summer, and winter lecture series, 10% discount on most purchases, a share of the stewardship, and reciprocating privileges to more than 345 gardens nationwide. Mary Spring is a 501c3 nonprofit organization primarily funded through memberships, grants, and donations. You can donate securely online at maryspring.org. You can give us a call with your credit card at 207-236-2239 or mail your check made out to Mary Spring Nature Center and send it to P.O. Box 893, Camden, Maine 04843, and we thank you. This presentation was originally recorded on Tuesday, April 1st, entitled Ice Age Cycle, presented by Sean Birkel of the Maine Climate Institute, and Sean is the State of Maine Climatologist. Previously recorded Tuesday talks uploaded to Mary Spring's YouTube channel are generously sponsored by the Cascade Foundation.
Okay, so Ice Ages in Maine's Landscape. We'd use a number of different titles, but I think this encapsulates it. What I would like to do for the next, for this talk is to share with you a little bit about the Ice Age history of Maine's landscape and spend some time first talking about Ice Ages in general, when they occurred in the timeline of Earth's history, and why an ice sheet formed over North America, for how long. Something about discuss a little bit about the evolution of the ice sheet over North America over time, and then the landscape that has been left behind since the last glaciation, which over Maine ended between about 14,000 and 12,000 years ago. And as you can see on this title slide, the pretty stark difference between a landscape glaciated with an ice sheet. On the left, that's from an image from Antarctica, photographed from my graduate advisor, George Denson. And then on the right is Katahdin from several years ago, a beautiful day for a hike in May when there's still some nice snow cover. There are these large bowl-shaped depressions etched into that landscape, and those are called cirques. And those once held glaciers, and beyond that, this entire landscape was once covered by a vast ice sheet. So the amounts of change over time is quite remarkable. For the presentation outline, I'd like to have a few more introductory comments, and then we'll go on to Pleistocene ice ages. We'll define Pleistocene so that what we know of past ice ages, plural, because there have been several, they're quasi-cyclical. And then the Laurentide ice sheet, that is the ice sheet that grew to cover much of North America, more than a third of the continent. And it was the largest of the former ice sheets, larger than the present day Antarctic ice sheet. And then we'll explore Maine's glacial landscape through photographs. And to wrap it up with Q&A, If there's time, I could potentially also uh, open up Google Earth and we could poke around and see some of the interesting features that are readily available in Google Earth, and some of these little details that we can find is just amazing. And so I'd like to give you a little bit more information about what I do as a state climatologist, and also at the University of Maine. I'm an assistant professor with a joint appointment between the Climate Change Institute and Cooperative Extension. And for the Climate Change Institute, or CCI, that is a research appointment. I study long-term climate variability, um, as well as I study weather as well. And I use climate models, gridded data, and I develop climate data visualization products. And as a state climatologist, I provide what's called climate services, and that spans both the weather timescale and climate timescale. And the purpose of climate services is to assist in the production and delivery of climate and weather data, developing products for Maine stakeholders to inform decision making and planning. And again, that's on both the weather timescale and the climate timescale. And I've had a long time affiliation with the Climate Change Institute. I was a graduate student here, and many of the slides that I show you will be were produced as part of my work as a graduate student. And these days, in the last decade or so, I've been more focused on modern climate, the changing climate, and research on these issues. But as a graduate student, I spent many years on paleoclimate, and in particular, investigating the last glacial cycle over North America and ice ages in general. Why they happen? What are the complex processes involved in which the Earth, through time, sometimes cools to the state where large ice sheets form over parts of Europe and North America, Siberia, and then they wane. It's a very interesting story, and it's part of long-term natural variability, and it can help inform what we understand of the changing climate from human causes. And so the Climate Change Institute is among the first multi and interdisciplinary research institutions in the country, as well as worldwide. The institute was founded by Hal Borns, who passed away a few years ago, but in the early 1970s. And a year ago, we celebrated our 50-year anniversary as an institute. It was originally called the Institute for Quaternary Studies. Quaternary referring to the past 2 million years of Earth history. And then it became the Institute for Quaternary and Climate Studies. And then in the mid-2000s, we changed our name to the Climate Change Institute. But it's the same institute, and I've been a part of it for a long time, and I'm eager to share some of the work that I've done. And I want to note that the Institute has many different disciplines within ice core research, glacial geomorphologists, paleoecologists, as well as climate monitoring and prediction, and ecological monitoring. There are people who investigate migratory birds and lake ecology, people who work on pollen analysis. And as you can see in this map in the corner, these dots indicate all the different locations that researchers, both faculty and graduate students, have worked in for this variety of research. And again, as I mentioned, much of the work I'll be presenting relates to my graduate research, and including my PhD dissertation. And I want to mention mentors along the way who, as I was researching paleoclimate. Um, these individuals I learned an immense amount from and had opportunities to do field work, for example, in the Antarctic dry valleys during the field season of January, February, to January, February 2003. It's hard to believe how long ago that was, but and that was with Dr. Brenda Hall, and also George Denton was involved in that. Terry Hughes, as you'll see in a couple slides, he passed away a few years ago, but he was one of the key individuals who developed the marine instability hypothesis, why large ice sheets can become unstable. And that's a concern in the Antarctic now, for example. And you'll see how that relates to the Laurentide ice sheet, as well as my PhD advisor, Peter Coons, uh, who works in geodynamics, James Fastook, who developed the Maine ice sheet model, and I use that extensively in my research, as well as my postdoc mentors, Kirk Mosh and Paul Majewski. And it's just been a remarkable journey learning about the climate system, and now as a faculty member myself, continuing on as a climate researcher. But putting together this talk was really a lot of fun because I haven't presented on paleoclimate in quite some time. So looking through some of the old photographs and results here too. I mentioned in 2003, as a graduate student, I had the wonderful opportunity to participate in field research in the dry valleys of Antarctica. We're collecting cores from lakes. Believe it or not, there are lakes in the Antarctic. In the dry valleys, they're capped by a cover of ice about 20 feet thick. We had to drill through the ice, send the core bill down through up to about 70 feet of water, saline water. It's liquid because of the high salt content, and then put the core barrel down into the underlying sediment and pull all that up, and where that could be analyzed for grain size and composition. That overall this would provide something about the flux of water into the lake, how it changes over time, and helps us to reconstruct the climate of that particular area. And a few years later, I was fortunate to participate in field research in the Wind River Range, Wyoming, and that was to study the past extent of alpine glaciers in that region. And there was a technique that could be used in the laboratory to find out how long a particular boulder that was deposited by a glacier had been sitting on landscape, so we can construct a chronology of ice retreat in the area. And it's a very beautiful place. Both those places are quite beautiful, and I feel very fortunate to have had the opportunity to participate in that work. My primary role was using the University of Maine ice sheet model to simulate past ice extents using numerical model, solving physics of ice flow, as well as accounting for changes in temperature and how that affects what we call the mass balance of the glacier. The mass balance is the accumulation of snow, and how that is balanced out by mass loss through primarily melting. Also, there's also sublimation, which tends to be pretty minor in most cases, but that's where this ice in the solid form can go right to a vapor. But the mass balance, snow accumulation in winter for temperate glaciers, and then the melting that occurs in summer. And it's that balance that determines whether or not a glacier expands or contracts. And as the climate warms, on a given glacier, the mass balance is changing such that there's less and less snow that accumulates overall, and there's a larger amount of ablation. Now, this is true for alpine glaciers in the mountains, for ice caps, such as shown here. This is the Wind River Range in western Wyoming. Here's the modern landscape as shown in Google Earth. And then here's a reconstruction of the last glacial maximum ice extents of the Wind River ice cap. And that was on the order of 17,000, 18,000 years ago. And so now, having given you some of that background to define the Quaternary period, the last approximately 2.6 million years of Earth history. A lot of information on this chart, but to step through it, this is a geologic timescale um, from captured from Encyclopedia Britannica. It's a really nice representation. Um, and so the earliest is on the left and to the top, and then the oldest 4.5 billion years ago. So these are the divisions that geologists have been able to reconstruct through great effort over more than a century now of research from people all around the world, studying rocks, figuring out how to age date them using radioisotopes, and looking at fossils and identifying different strata, uh, establishing the similarities between landforms on one continent versus another, an immense amount of human effort to understand Earth's history to the extent that we now understand it. So now if we go to the Cenozoic era, we're going to focus on the Quaternary period, again, the last 2.6 million years of Earth history. And when we talk about ice ages, this is the time that we're talking about, is during that period where periodically Earth became either had more or less ice extent. And the Pleistocene ice ages in particular, and especially the last million years or so, there's been a series of ice ages with an approximate fluctuation of 100,000 years. It's not exact, it's quasi-cyclical. And then the last major glaciation, which lasted about 100,000 years, that ended rather abruptly about 10,000 years ago, and you'll see more about that soon. And then the last approximately 10,000 years of Earth history is what we call the Holocene epoch. We also, as paleoclimatologists, we refer to it as an interglacial period, as opposed to a glacial period. Okay, and so now to explore that a little further, if we now consider the Pleistocene glacial cycles for the last approximately 750,000 years, so we're taking a shorter, somewhat shorter look onto that time scale. And so here at the bottom are two time series of proxy data that provide some information about past climate. At the top is a proxy, some of record that gives us information about what the global ice volume and or sea level may have been. And this is from a deep sea sediment core in which these composition of foraminifera were identified. And depending on the composition, it's possible to determine whether or not these creatures formed in either cool or warm conditions. And so it's possible to reconstruct these fluctuations over time using this proxy record. And so over here, you can see that the bottom of this time series represents the glacial periods versus top, these are the interglacial periods. So you can see there's quite a transition in between the two. And it's quasi-cyclical, but the interglacials, for the most part, tend to be fairly brief. One could say that the full glacials also tend to be fairly brief. And then there's this the transitory or transition period that's quite long time scale. And now at the bottom is a different proxy record that provides slightly different information. And this is from an ice core that was recovered from Dome Sea in the Antarctic. And this examines isotopes of, it's called deuterium, which is an isotope of water. And based on the signal of deuterium, it's been found that that is linked to air temperature. And then as snow accumulates over the Antarctic ice sheet and eventually turns to firn and then to ice, air can be trapped in the ice and in these bubbles of air. And then when an ice core is collected, those air bubbles can be we can determine what the composition is and then develop proxy records. So what's interesting is when this Antarctic temperature proxy is compared to the global ice volume proxy, there are clear similarities, which then helps to support that this Antarctic temperature, in a way, could be a proxy for global temperature. We'll keep it at the Antarctic temperature, but there's a clear connection to the global sea level change. And so climate scientists use different records, different proxy records from many different places around the world, and not just in ice cores, not just in deep sea sediment cores, but also pollen records, and even from caves, from stalactite and stalagmite records. And more recent, for records that go back several hundred years, we can even use tree ring records, all to try to understand how the climate is changing over time. And just to note, this map up here shows the approximate extent during what we call the last glacial maximum, and that was 24,000 years ago. And so that would be the glaciation that is identified here in these proxy records. And I should have mentioned at the start, in the paleoclimate literature, it's common to go from left to right, with left being the oldest and right being the youngest. So it's backwards from, actually, in this case, it's not backwards. Some of these, you might find it flipped, because much of the paleoclimate literature has the youngest on the left and the oldest on the right. So I apologize if I just added some confusion there. Okay, so the Wisconsin glaciation. That's this last phase of glaciation over North America, the last 100,000 years. And the Wisconsin glaciation, because of the extent of the ice into what is now Wisconsin. And there were four primary ice sheets here. There are three listed in this particular figure. The Laurentide ice sheet here over North America, over what we call the Canadian Shield. Really in many ways, the center of the continent, centered on Hudson Bay. Then the Cordilleran ice sheet, which primarily formed over the mountains, would have started as ice caps and alpine glaciers that expanded. The glacier that covered the interior of Canada was very different. That was an ice sheet that formed over lowlands, which is something we'll get back to. The Greenland ice sheet, it was more expansive at the LGM. The ice had expanded to what we call the continental shelf. But that ice sheet, of course, is still there today. So in a way, there's still some of the ice age is still left. And then up here, it's not labeled such, but this was often considered a separate ice sheet called the Inuitian ice sheet. But these were connected, and there was coalescence of ice. And then there would have also been floating ice shelves over the Arctic Ocean, and other areas where there was not ice shelf would have been sea ice. And let's see, proceed. Now, why did these ice sheets form, and why do they disappear? Or I shouldn't just say disappear. They don't disappear, but they ablate, and they'll expand and contract. Well, the dominant theory, this was first set forth by Milankovitch in the late 1800s and the early 1900s, who developed the theory of ice ages based on changes in the orbital parameters, Earth's orbital eccentricity, and that is how circular or elliptical the shape of the orbit is. That has a wavelength of about 100,000 years. orbital obliquity, which has a wavelength of about 41,000 years, or I should say period of 41,000 years. And that's the axial tilt, ranging from 21.5 degrees to 24.5 degrees. And so that would, just to try to picture that, that affects the noontime sun angle. It's either the sun would be lower in the sky or higher in the sky. And this oscillation is every 41,000 years from one peak to the next. And then there's also precession, sometimes called precession of the equinoxes. And that is where in its orbit, so there's the axial tilt, where in the orbit the at this with this for the same tilt axis, it's either happening when the Earth is at its closest point to the sun in its orbit, or the farthest, depending on. I hope the graphic, I hope it's making up for my lack of words at the moment. But that has a period of 19 to 23,000 years. Now, when those three components are integrated, that provides that is how we define summer insolation. That's the overall amount of heat in watts per meter squared that is received at a given point on the Earth's surface. And it's commonly in the paleoclimate literature to focus on 60 north when we're seeing how this might relate to the buildup of ice. The insolation signal is shown here. And then if we look at a composite reconstructed global sea level record, you can start to see that it looks quite similar. The insolation in the northern latitudes versus the global sea level reconstruction. And so paleoclimatologists generally now accept that insolation is an important part of the picture, but it's obvious that these are not exactly the same, these two signals. There are feedbacks in the climate system. There are nonlinear processes involved. Ice sheets interact with the atmosphere, with the ocean, and changes in climate occur with changes in the greenhouse gas composition, changes in water vapor, CO2 and methane as well. It's all part of the story. It's beyond the scope of this talk, but the natural climate variability involves insolation, and it also involves all the complex interactions within the climate system. And that is what provides us very useful and important context for understanding how humans are now impacting the climate system by introducing CO2 and methane into the atmosphere well beyond any historical or long time scale background. And so now we're getting close to the photographs of the Maine landscape and what this means for the Maine landscape. A couple more slides of background, though. So the last glacial cycle, going back a little more than 120,000 years ago. And here's what we call the last glacial maximum, again, 18 to 24,000 years ago. And then this is what in the literature is called the glacial termination. It's called a termination because it happened relatively quickly. Within about 10,000 years, Earth's climate went from a full glacial to an interglacial. And enormous amount of changes occurred in terms of sea level, because as ice sheets, as they accumulate on the Earth's surface, the water with that ice constitutes comes from the oceans. And so the ocean level drops as more water is being retained as ice on their surface. And so when ice sheets decline, the sea level then rises. And then for the Holocene period, sea level hasn't changed much, because once the large ice sheets had withered away, the other ice caps and the Greenland ice sheet stayed relatively stable. And so this map is from 1973, showing the outer extent of ice that has been mapped for the last glacial maximum, as well as I wanted to show this because these different uh, uh, color separations show the approximate time intervals. So, for example, this light blue here represents the period from 13,000 to 18,000 years ago. So that's when ice, which had extended to Long Island, New York. Long Island, New York is built of moraines at the terminal end of the Laurentide ice sheet. And then the terminal end extended into Georges Bank, which is now below sea level off Gulf of Maine. So the ice had retreated across this area from about 18,000 to 13,000 years ago. And then in this medium blue, between 10 and 13,000 years ago. And then when we get into Canada, to Quebec and Labrador, this band of blue represents ice that retreated between 7 and 10,000 years ago. And then 6 to 7,000 years ago, there was still some ice left over central Quebec, as well as over this area here to the west of Hudson Bay. This is an area called Keewatin. And there was also remnant ice over what is now Baffin Island. And in the dark blue, these are ice masses that are still present today. And I'll note that this ice mass, this is called the Barnes ice cap. That is a remnant of the Laurentide ice sheet. It still exists on Baffin Island today. It's melting, it's losing mass, and in a warming climate, it may have a few hundred years left, but it is declining. We look at Google Earth imagery, you actually see how the margin has contracted over the past few decades. And there's also the penny ice cap over here. But the Barnes ice cap is especially interesting because there's Pleistocene age ice that in the 1970s, it was sampled. It was dated to the Pleistocene. So there's ice that fell in this area, or snow that fell, and it's still now ice in that ice mass. So it is a remnant of the Laurentide ice sheet, which I've always been quite fascinated by that. Okay, and now I mentioned these complex processes for ice sheets growing and contracting. It's interacting with the broader climate system, with the atmosphere, the oceans, with the atmospheric composition. And now one of the fascinating aspects of how the Laurentide ice sheet vanished, I use the word vanished, how it retreated in such a rapid time. It's been known now for a few decades that large ice sheets can grow to become unstable if they become grounded below sea level and if their margins interact with ocean water. And there are calving fronts in which, if there's sufficient melting and moving of a calving front, it can get into a situation. And so now we're going to go over to this panel on the right. If we look at, here's Quebec, here's Baffin Island, and here is Hudson Strait. We know from mapping that there was an ice stream, that's a fast-flowing river of ice, that was positioned here, and it was buttressed by a floating ice shelf. And from radiocarbon dating of shells, from which it becomes possible to identify where this ice margin was retreating and when, it's been found that the ice margin, the calving front, retreated quite rapidly through Hudson Strait. And the hypothesis is that there was a buttressing ice shelf that slowed the flow of this ice stream, and that if for some reason that ice shelf was lost, the flow then accelerated behind it and enabled the ice margin to calve farther and farther back towards the center of the ice sheet. And now, because as ice accumulates on the landscape to great depths, that mass then pushes against the Earth's surface, and the the crust in lithosphere, it gets depressed, and the base can become lowered with respect to sea level. So it forms a bowl-shaped depression. The ice accumulates more and more and more, and it becomes depressed or further and further below sea level. And so then this process can, in the case of the Laurentide, appears to have excavated the interior of the ice sheet through this mechanical process. And then the climate system is, because it is coupled to this massive ice that is interacting with the atmosphere and the oceans, the climate system then adjusts to that. And there are these feedbacks that occur. But what we result with, excuse me, now just to add some modern relevance to this, here's a recent article: Antarctica's Thwaites Glacier ice shelf could collapse within 5 years. Maybe it will, maybe it won't. There's active research trying to understand whether this particular ice shelf may decline soon. And the importance is that there's a large amount of ice behind it that could then become excavated quickly and increase the rate of sea level rise. But this goes back to the original work of from Denton and Hughes. Also, Terry Hughes' mentor, Hans Bertmann, developed the initial hypothesis, and then Terry further developed it and suggested in the 1970s and 80s that parts of Antarctica, especially the West Antarctic ice sheet, could be susceptible to the same instability that removed the Laurentide ice sheet from North America. Here's a simulation, and this is something that I made as part of my PhD work in the late 2000s. This is a deglacial simulation of the Laurentide ice sheet, and it demonstrates this instability that occurs over Canada and Hudson's Bay. And note that in the simulation, the Greenland ice sheet does not disappear. It stays here, because in this particular simulation, it does not appear to be unstable, but the Laurentide ice sheet was unstable. And now, just to highlight that further, this is from a World Atlas, 2002. I happened to see this, and it just struck me this is a really important visual. Now, if we look at the Greenland ice sheet here, north of 60 degrees latitude. And now, if you move your eye along these lines of latitude, move to the west, note that this area, which had previously been covered by the Laurentide ice sheet, that is now deglaciated, but the Greenland ice sheet remained. And so that highlights, again, there was something different about North America that enabled the large ice sheet that once existed there to collapse, whereas the Greenland ice sheet did not collapse. It contracted, but did not collapse. And then finally, before we get into the main geology part, this is a satellite image, a composite. From NASA satellite data, this represents May 2004 snow cover over North America. And we can see signs of the Ice Age in the modern climate. In a way, the Laurentide ice sheet tries to come back every winter. The climate's too warm, and so there's winter snowfall, there's accumulation, but into the spring and summer, the heat is such that the snow melts, and the climate is not cold enough to support an accumulation from one season to the next, to the next, to the next. But the overall footprint of the ice sheet reforms every year. Maybe I'm getting a little philosophical, but I just thought this image is really quite fascinating. Okay, so now we're going to shift gears a bit and look at examples of what the glaciation of North America has left as an imprint on the Maine landscape, starting with the Maine Superficial Geologic Map. And this is from has been compiled by a number of different people in the Maine Geological Survey. And one thing to note, this blue line here represents what is understood to be the sea level high stand. So when the continental ice, a lobe of the Laurentide ice sheet, retreated northwestward across the state, the ocean water was in contact with that ice front, and for a time, sea level, the ocean had inundated these areas that are south of this blue line, and so we can find, for example, in the shade of pink, glacial marine deposits, silt and clay. So if you have silt or clay in your backyard, that's that was deposited in a shallow marine environment after the ice had retreated. And there's also sand and gravel in this darker magenta color. Down east, where wild blueberries are produced, sand and gravel deltas are a really important substrate that wild blueberries thrive on. There are these glacial marine deltas that are now wild blueberry fields. And you can even see areas where wave eroded bluffs have been etched into the sides of these features when there was, again, a shallow marine environment. And so now here. So Maine's landscape 20,000 years ago looked something like this. This is actually a photograph from the Antarctic. Now, if we take that ice off, now we're now taking a look at a part of East Greenland, and you can see a lobe of the Greenland ice sheet off in the distance. But this was formerly glaciated, but the ice has been removed, and below it we see what is called an aerially scoured landscape. There are depressions which fill in with water, become lakes and ponds. There's this complex topography because of erosion that takes place under the ice sheet. And then if we look at down East Maine, for example, we look at a map of Maine in general, we see all kinds of lakes and ponds, many of which are dammed, but the basins, the depressions that were formed that can now hold water, those were scoured beneath the Laurentide ice sheet as it flowed across the landscape. And so we can compare and contrast. This section of East Greenland shows that aerial scour, and this aerial scour is also shown across a good portion of Maine. And I couldn't find the animation that I put together all those years ago, but I did find the slide with still frames. I had taken the Maine relative sea level record that was had been reconstructed by Dan Belknap and others, and Joe Kelly and many other people contributed to by measuring shorelines and getting radiocarbon dates of shells to understand how the sea level changed over time over Maine. So this goes back to about 16,000 years ago, and we find that there was a sea level low stand about 12,000 years ago, and then sea level rose back up, and eventually we get to the modern condition. But I just wanted to point out, so as Mount Desert Island was deglaciating, and there's evidence that Sargent Mountain Pond, for example, that may have been the first or one of the very first areas that became ice-free during deglaciation. And Steve Norton and others have conducted analysis of the pond by taking core samples to determine at what time the deglaciation occurred. But so here we have sea level 65 meters, which has been about 300. If we translate this into feet, the global sea level was about 300 feet lower at the height of last glaciation than it is today. But here are three separate stages. Maximum glaciation, or near when the ice was retreating across Mount Desert Island. Here's the sea level low stand, when sea level was lower, and much of what is now water was actually land. And then here's the modern coastline. And now if we zoom in, I'm looking at time. We're definitely not going to have an opportunity to look at Google Earth, but I will get through all my slides. This is from Our Maine, a wonderful book that was published last year that has an in-depth overview of Maine geology, as well as glacial geology, ecology. It's a really beautiful book, and I was fortunate to have been able to contribute a small part of the climate section. But this particular image is from LiDAR imagery, that's from laser altimetry readings on the left. And this is for the Trenton area. So here's Mount Desert Island in the southeast corner. Here's Trenton. And now this is a little confusing. It's not a comparison of the same place. This is Lincolnville, and then Belfast is up here to the north of the image on the right. But it's a comparison of two different resolutions, and that this LiDAR imagery on the left, it can resolve meter scale features in the landscape. And do you see all of these lines, those hash marks? Those are moraines that were formed. The interpretation is that these are annual features that track the annual progression of the ice margin northwest across this area of the state. So there's potentially an annual record of the retreat of the Laurentide ice sheet over this area. And these features are only about 5 feet high. You can walk through the woods and not really notice them, but with LiDAR imagery, they become quite apparent. And this was probably about a decade ago, maybe a little more than a decade, that the LiDAR imagery first started to appear. And people were just absolutely amazed because we started seeing things that we were unaware of until this particular technology can see through the tree canopy. And so it has a really high fidelity in picking up some of these subtle glacial features. Now I'm going to go through these slides really quickly. Here, moraines. These are features that are formed at the end of a glacier, either on the sides or at the terminus. And it's the material that has been either fallen onto a glacier surface or ground up at the base, but eventually gets deposited in what we call moraines. This particular example is from the Southern Alps in New Zealand. And this is another example from East Greenland. Here's a lateral moraine. In the next figure, finally, we're getting to Maine. Here's Katahdin from approximately the east. There's Baxter Peak, there's Pomola, and anyone who's hiked up into the Great Basin has gone past Basin Ponds. This is the Basin Ponds moraine. This was a lateral moraine formed when there was a lobe of Laurentide ice in this area here. And then also there are these bowl-shaped depressions called cirques that sometime in the past also had ice flowing out of them. And so here's another view of that, these wonderful, well-defined cirques on Katahdin, as well as other places in the Northeast and New England. Certainly Katahdin. There are some cirques out in Western Maine as well, around Sugarloaf and the White Mountains, a number of examples of cirques, a couple in the Green Mountains, the Adirondacks, and even in the Catskills. And then here's Wind River Range, Wyoming. This is a small glacier that in a cirque, and I thought this was kind of an interesting comparison. Just imagine at some time glaciers sitting in these cirques. Now, because of the continental scale glaciation, at some time all of Katahdin was covered. Other times, part of the mountain was emerged from the ice, and there may have been some interval. So when these cirques were filled with ice, it may have been when there was also a lobe of continental ice. That still hasn't quite been fleshed out. were there isolated glaciers within those cirques without there also being continental ice? Still not quite known. Another example of a cirque in the Wind Rivers. And then here's Chimney Pond in this wonderful head wall, as we call it, just below Baxter Peak. And also frost shattered bedrock that's the trail leading down from Hamlin Peak. And frost shattered bedrock, that occurs in Arctic environments. You'll find it actively occurring on Baffin Island today. It's where the annual temperature is well below freezing, 10 degrees C below, and where there can be extreme freeze-thaw events where water will cool below the freezing point quickly, and the expansion of water into ice will break apart the rocks. So this is when we see an alpine landscape on tableland landscapes, we see frost-shattered bedrock. And here's an example from higher elevations in the Wind Rivers, and in here, the tableland of Katahdin. Another example from Katahdin's tableland. Then also from glaciers eroding the surface, creating striations that we can see here, but also the landforms. So we call this a roche-moutonnées, and they can be at a small scale. They can also be at a very large scale too. But you can see here ice flow from left to right in this picture, and this is the Stoss side, and this is the Lee side. So the Lee side is very steep facing. This is at the outcrop scale, and you can see a pen or pencil here scale. Now, at a larger scale, here's the owl in Baxter State Park, adjacent to Katahdin. And notice the same overall morphology as this. Ice was, we can see what the ice direction was. The ice, in reference to this picture, is going from left to right, and on the lee side is where boulders were being picked off the ice, the mountain face. And then the picture below, this is showing looking at the owl from Katahdin. So the camera is roughly about there, looking towards the owl. Erratic boulders that we will often find in the woods in Maine, those have been transported some distance by glacier ice. A really large erratic probably hasn't gone that far from the source, but if it's a boulder sitting on a different bedrock type, then you can figure out where it may have come from. Here's a U-shaped valley. This U-shaped landform, that's when there's a valley glacier eroding at the base. And here's an example. This is also in Baxter State Park. Here's Double Top Mountain. This is on the east side of the park. Here's a wonderful U-shaped, this would be a U-shaped col. That would have been continental ice flowing through it. And then Nessewadenhunk Valley is also nicely U-shaped. And then in this photograph, there are erratics. Technically, an erratic is when a boulder of one bedrock type has been moved and is found on another bedrock type. These aren't quite erratics by that definition because it hasn't been moved far from the source and it's the same bedrock type, which is granite here. So I'd like to end with just noting Maine's Ice Age Trail Map. This was spearheaded by Hal Borns and the Climate Change Institute, and it has a tour along many parts of Maine, especially along the down east coast and in other areas where you can visit different kiosks and learn more about the glacial features there. It's on the Climate Change Institute website. There's an app that you can download, and there's also a map that I believe we still have hand maps that can still be purchased. And with that, I'd just like to mention Maine Climate Office, mco.umaine.edu, source for Maine climate data, and as well as weather forecasts. And given the time, I just want to move on to say thank you And I realized I went a little bit longer than I wanted to for talking, but we still have a little bit of time for questions. And I'm happy to stay past the hour for anyone who has questions. Thank you.
Excellent, Sean. Thank you. Excellent. Yeah, I've got a list, which we'll talk about next week. But fabulous and very, very informative. Now, so when we are looking, because I'm going to ask a question real quick. So when we're talking about orbital variations, and then you've got precession and obliquity and et cetera, you also you could add on to that continental drift
Over
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 millions of
longer,
years.
yeah,
But
um,
but
yeah,
maybe
because
they don't move much in 100,000 years.
well, 65,000 years ago, for example, when it's understood that the dinosaurs went extinct, that was when Africa and South America were still together. They're, as I recall, just starting to separate. And so, but that's 65 million years ago. And so just imagine how long it would take to go from that situation, which was at the breakup of Pangea, to the current configuration over 65 million years. And the Quaternary is roughly 2.5 million years. And so there would have been some,
Yeah.
the kind of configuration would have been a little different than it is now, 2.5 million years ago, but closer to what it is now than it was um,
Okay.
4 million years.
Yep. No, that makes good sense. Yep. I was starting to think about how you'd have the continents being closer or further from the equator, and
Oh, absolutely. Actually, this is a very important part of the story because one question is, well, why prior to 2.5 million years ago were there not large ice ages? And so the dominant interpretation is that it's the changes in the shifting plates and the change in configuration of the continents in ocean, that different configuration that has enabled large ice sheets to form. And part of my dissertation examined this. I did a literature review, and my feeling is I agree with that hypothesis. It seems as though the expansion of the Laurentide ice sheet in particular that developed because of the unique uh, continental configuration of North America, the size of North America and its relation to the westerly jet stream as it comes off the Pacific and the Western Mountains. It forms a ridge of warm air over the west and a trough of cold air over the east. If I almost put this in, but I had too many slides as it was. If we look at the jet stream today, just the average position of the jet stream in say April, it outlines the Laurentide ice sheet very nicely because that ice sheet formed beneath polar air masses within that trough. And so, and this is described in my dissertation that one of the feedbacks that I propose is that the ice sheet expanded beneath this cold air circulation, and there was a feedback that also involved the North Atlantic Ocean downstream. And that once something can nudge the system towards cooling, well, then more ice accumulates, and that reinforces the atmospheric pattern, which cools the North Atlantic downstream. And so this may have been part of why the Laurentide grew as big as it did. And but so getting back to your question about plate tectonics, that that seems to be an important piece to why the ice ages began, is because of the particular arrangement of the continents favored with these large land areas in the wintertime, there's radiational cooling. So if the configuration is such that most of the land is more towards the equator or the tropics, then far less likely to get any kind of glaciation.
yeah, interesting. Wow. We joke about the glacier in the driveway. Got another question for you about the bedrock recovery.
Yes.
And so if out to George's Bank was dry land, and I think they found evidence of fires, people having fires and things like that out there. Because that is not rebounded and is dry land, is the weight of the ocean holding that down?
Uh, that's a very good question. The there would be some impact. I don't know quantitatively. I'm not sure,
Yeah.
um, but um, I know people. There are people who I could ask to get a clearer answer, but it does constitute a mass, a weight, and so there has to be some adjustment for that.
Mm.
But I guess the difference would be the accumulation of this mass over dry land and um, how the long story short is there has to be an adjustment, some compensation in the lithosphere for the mass of water. Um, but I haven't quite thought of the dynamics of the water mass impacts on the lithosphere versus the retreating ice. That is interesting to consider.
Yeah, no, I was just wondering. And I guess if we wanted to find out what was in Maine before the last glaciation, we could go dig down in Long Island and Cape Cod, and maybe there's stuff that got scraped off here because there was nothing left, right?
Yeah, and this is fascinating. There are in some areas, there have been older tills. I should have defined till. That's material that covers much of Maine, and it's material has just been ground up at the base of the ice sheet, and there isn't any particular organization, um, and it's just what's left behind. Especially, it appears as though till seems to form when ice ablates quickly, and so therefore it's not deposited in these nice layers or strata that can be identified. It's just kind of deposited all at once. So much of the state appears as though at some stage in the ice retreat there was widespread ablation and the ice just melted down and then that material's left behind as till. There are some locations in which older tills have been identified based on the basis of weathering and perhaps other means, but and I don't recall exactly that there are a couple sites in Maine and elsewhere in New England where there are tills thought to be from the past glaciation. But it's few and far between because of how much scouring takes place, and so much of the record of past glaciations has been eroded and replaced by the more recent glaciation. Another way we can also, on some surfaces, and I didn't include one of the pictures, but on some rock surfaces, you can see different striations in completely different directions, indicating a change in ice flow. And then at the landscape scale, if we were to look at Google Earth, and if we look at some of the Canadian landscape that has much of Canada and around Hudson's Bay has only very thin soils or no soil at all. It's because it's a cold climate and it's just been scraped down by so many glaciations. But you can see these large scale features indicating ice flow, and you can see in some places you can see two different ice flows completely across one another, and geologists have used this to map out past flow regimes and where there may have been an ice dome that would have produced that flow versus another one. And that map I had shown towards the beginning of the talk, it was a die-compressed, I think, 1973. On that map, if you look closely, they also have show the flow directions. You'll see where some of those do the
Okay.
crisscross.
Yep.
So it's remarkable that these features at different scales can be preserved even after a different flow regime.
Wow. I'm going to let John Brock, I'm going to ask John to unmute, and he has a question.
Yeah, hi. Nice to meet you, Sean. Really great talk. Really found it very interesting.
Thank you.
I have a few questions, but I also noticed there's some folks in the Q&A list that had some
Yeah.
questions, so maybe I should let you answer those first.
Oh, okay,
Would that
sure.
be all right?
I can read Ray's questions. Yep. So Ray said, I apologize if I missed it, but I didn't see on your maps any ice sheet across the Bering Strait, which allowed the first Americans to enter the Western Hemisphere from Asia. When was the Bering Strait frozen over? And he says, or am I mistaken, was there a land bridge between Asia and America that was later frozen over or submerged?
The land bridge was at the sea level low stand. There was a Bering land bridge, and it was not glaciated. And however, getting back to the Cordilleran ice sheet that formed over the Western Mountains, um, the Beringia, as we call it, and I'm hoping that I don't miss any details because it's not an area that I have studied in detail. But in general, uh, Beringia was opened. This land bridge. It was a relatively dry climate, but because of I mentioned the ridging of warm air over the west, that could produce glaciation in the mountains. But a combination of the relatively warm airflow, it was colder than it is now, but it was relatively warm compared to what eastern Canada got in the trough. The with the dry conditions, that was insufficient to produce a widespread glaciation over the lowlands. And so with the lower sea level, there was exposed land that was unglaciated. As far as I am aware, again, I may, at least for the last time that it had opened up, 18,000 years ago or so. But at that time, the Laurentide ice sheet and the Cordilleran ice sheet had coalesced. So people would not be able to just, you could not get from the unglaciated interior Alaska to what is now the lower 48. That would have been completely blocked by continental ice. And at some stage, those two ice masses retreated and a corridor opened up. And there's a debate about how the access would have been, because if you go to an ablating glacier in the modern climate, if you go to a ablating glacier now, the terrain is a mess and it's extremely difficult and dangerous to travel. And it's uncertain for how long this corridor would have been in that state, and this is now beyond I'm not familiar with the most recent literature on this. There's also a hypothesis that the travel could have been along the coast. But I don't know the current consensus on this, or the more recent debates, where I haven't been reading this literature for 10 years or so. Wow. But it is fascinating. It is really a fascinating development of the opening of this land bridge from the sea level low stand. And when could humans either travel along the coast and or through what eventually became an ice free corridor? And but it's certainly an important part of understanding the peopling of the Americas.
They had to be rugged.
Yes.
Yeah. So last question, and we'll go to John. What are the predictions for the demise of the Greenland ice sheet?
It's uncertain whether or not the Greenland ice sheet is susceptible to a mechanical collapse, as I outlined. Now, the ice sheet does, if we were to, bathymetry has been identified using ground penetrating radar and in gravity studies as well. Greenland is sitting in a bowl-shaped depression that is below sea level. So there is this potential for instability. However, there's only one or two channels for which this calving process could propagate into the interior. One is the northeast channel, and I forget where the other one is. Now, many groups have modeled the Greenland ice sheet. You will find some papers that suggest it's stable. You'll find others that suggest it could be unstable. And if it is unstable, it all depends on the temperature, mass balance threshold, and where there are what we call pinning points. And if an ice stream, if the calving front moves past this bedrock pinning point into, again, where it gets into this depression area, there is definitely that potential, but we don't know for certain yet. It could be hundreds of years, it could be 1,000 years. But again, I will just follow that up with I'm not up to date on the most recent literature on the Greenland ice sheet. For the simulations that I did using the Maine ice sheet model, and it's unpublished, so I don't want to overemphasize this, but um, I think it's probably stable. But we can also look to the last interglacial, which was warmer than the present interglacial. It is understood from the available evidence that the southern sector of the Greenland ice sheet had ablated, and so I think probably 2/3 of the Greenland ice sheet remain in the north. So it it remains a possibility that the ice sheet could become unstable and ablate quickly or through this mechanism. But it could also be that it just ablates more slowly and doesn't undergo a rapid collapse.
Okay, excellent. Thank you. John, go ahead.
Sure, yeah. So I had two questions, Sean. First one is I noticed on your 60-degree north latitude insolation time series graph that in the late Holocene, it looked like there's a drop in insolation. And so I was just curious, does that imply that if we didn't have all the greenhouse gases that we pumped into the atmosphere, that we'd actually be seeing a cooling trend now? That was my first
Yes,
question.
because this is in the scientific literature. There are many who have commented greenhouse gas emissions from human activity may have stopped the next ice age, um, and I think that's probably correct. But it is notable that even let's say if we were living 150 years ago, um, on the astronomical timescale, that's not much. And it's notable that the insulation today and at that time is about what it was at the height of the last glaciation. But the difference is the Laurentide ice sheet is no longer over North America. So the ice sheet, it's generally understood that the ice sheets, um, because of how they interact with the broader climate system, can become self-perpetuating. And as my former mentor, Terry Hughes, used to say, that the Laurentide ice sheet removed itself from the climate system. And now, for the ice sheet to reform, there has to be some kind of a nudge in the energy balance, in the heat balance in the climate system, that would cause a cooling sufficient enough to restart this process. And again, Terry Hughes, who I mentioned, he has a paper. I can't remember what it's called. This is from the early '80s. He hypothesized that the ice sheet formed out of Hudson Bay, and then I had started working on a paper building from that hypothesis, so that it may have started from sea ice thickening that eventually thickened to the point where an ice sheet would form and then start to cover the landscape, as opposed to in most areas, there are mountain glaciers that expand to form ice caps, such as the Cordilleran ice sheet and other places. But in Scandinavia, ice appears to, it may have formed from the Scandinavian mountains, but then it also engulfed, oh my gosh, I'm forgetting my geography here. Um, uh, uh, Across the Baltic.
Yeah. Okay.
In the Gulf of Boothia. So it appears as though for these large ice sheets, thickening sea ice could be part of it. And
Yeah.
I hope I didn't stray too far from your question.
Well, you did, and I can see how, and it's certainly the case that when you have a high reflectivity surface over a large area, you're going to have a positive feedback to create glaciation, because you're reflecting a lot of that heat away. So I had another question, and this is of interest to me because of the latitude that we're at here in Maine in particular, and the fact that it was under an ice sheet and there was, isostatic adjustment and then a rebound. And so I'm really trying to figure this out because I've been looking at some literature, and I noticed you had a map that showed a past shoreline, I think just before the beginning of the Holocene, that was inboard of where it is now. It's up in the interior of Maine, that shoreline.
Yes.
However, when you showed a relative sea level curve, I did not see a high stand at the same time. And that confused me because I think your graph did say relative sea level. So it seems like there would have to be a high stand to get that shoreline moved inboard. Maybe I'm not understanding that, but maybe it's hard to capture that high stand in a sea
Yeah.
level curve.
And I'll share my screen.
Sure.
Uh, let's see. Okay. So this would be the high stand. And I think I made this graphic, and I think it was probably around 2008. And to just give you a little uh, some background on how I made it, I took the modern topography with bathymetry, and then I I I used the values from this relative sea level curve, and then
Yeah.
for every grid cell, the sea level from the modern datum was adjusted based on this curve. But if we look
Right.
at the high stand, if you look at some of these features, you will see that, for example, the southwest portion of MDI is below sea level,
Right.
and
Yeah. So if I can just say, what I was expecting was a high stand just before the Holocene. So you have the high stand there that's, well into the Pleistocene, back that far. But I think from your map, as I understood it, there would be a high stand just before the beginning of the Holocene, because of the fact that the land was still depressed and hadn't rebounded yet, just after the ice had left it. But maybe I just need to look. Maybe I can talk to you next week about this.
and I yeah, absolutely, we can talk next week, and someone who would know a lot more about the relative sea level in this region is Joe Kelly, who
Okay.
he retired recently. I think he has emeritus status at EU Maine. He still
Yeah.
remains very active in the field.
Yeah.
But
Yeah.
Joe Kelly and also Dan Belknap were the.
Yeah. I had him for a class once, Dan
Oh, you
Belknap.
did? Oh, great.
Yeah, a long time ago. Yeah. All right. Well, thank you. I'll look forward to talking to you next week.
Oh, yeah.
Yep.
Likewise.
And Sean, thank you. That is excellent, very informative, and really appreciate it. So we will, John, you and I will talk next week, and we'll pick a time and get on that. And but thank you. This has really explained a lot, and it's to me it's interesting and really something to see. So thank
Well,
you.
you're very welcome. And as I mentioned, this was kind of fun because I really enjoy paleoclimate, and it's been quite a few years since I've had an opportunity to put together a talk of this sort. And uh, yeah, so I enjoyed it
Great.
and
Well, thank you.
appreciate the opportunity to present.
Sure, I
And I
appreciate
look
it.
forward to
Well,
next week as well.
yeah, yeah, good. All right. Well, we'll get in touch on that. And thanks to everyone who was here today. And we will see you next week.
Thank you.
Thank you for joining Mary Spring Nature Center's recorded Tuesday talks. For more information, please visit maryspring.org. We hope you'll consider supporting Mary Spring. You can donate securely at maryspring.org. Give the office a call at 207-236-2239 or mail your check to Mary Spring Nature Center, P.O. Box 893, Camden, Maine 04843, and make your check payable to Mary Spring Nature Center. Thank you, and we hope to see you again.